The unbalanced neutral current equation is derived by understanding the vector summation of phase currents. We'll start by defining the phase currents I, and IK, and assume they have phases of 0 degrees, 120 degrees, and 240 degrees, respectively. This is the standard convention for a balanced three-phase system. Next, construct a vector diagram. Represent the phase currents as vectors. I is on the horizontal axis at 0 degrees. I is rotated 120 degrees counterclockwise from I. IK is rotated 240 degrees counterclockwise from I. Now, we need to perform the vector summation of phase currents. The neutral current N is the vector sum of the three phase currents. The equation is N equals I plus IK. To proceed, square both sides of the vector summation equation. This gives us N squared equals I plus IK squared. Now expand the squared term using the distributive property. This results in N squared equals I squared plus I squared plus IK squared plus 2 times I plus IK plus IK. The term 2 times I plus IK plus IK represents the dot product of the phase currents, and it's important to simplify it. Since the phase currents are 120 degrees apart, the cross product terms IK when considering the phase angles effectively represent the real component of the product of two complex numbers. When summing these cross product terms, the sum will be equal to -1/2 times I plus IK plus IK. This simplification arises from the trigonometric identities associated with the cosine of 120 degrees, which is -1/2. When further manipulated, you arrive at the equation N squared equals I squared plus I squared plus IK squared minus I plus IK plus IK. The next step is to take the square root of both sides. This gives you the unbalanced neutral equation N equals the square root of I squared plus I squared plus IK squared minus I plus IK plus IK. It is important to note that the phase currents I, and IK are root mean square values. The neutral current N is the faster sum of the phase currents, and its magnitude is the root mean square value of the neutral current. The derivation takes into account the phase angles of the currents. If the currents were in phase, the neutral current would simply be the arithmetic sum of the magnitudes of the phase currents. However, because they are out of phase, the vector sum is used, resulting in a different final equation. The equation N equals square root of I squared plus I squared plus IK squared I times I plus IK times IK plus IK times I assumes that the phase currents are sinusoidal and have a phase displacement of 120 degrees from each other. The terms I, and IK represent the root mean square magnitudes of the phase currents. The neutral current N represents the root mean square magnitude of the current flowing in the neutral conductor. To use this equation, you need to know the magnitudes and phase angles of the phase currents. If you only know the magnitudes, you can assume a balanced system with 120 degree phase displacements. If you have unbalanced phase angles, you'll need to use a more complex phasor analysis. The equation is useful for calculating the neutral current in a three-phase system with an unbalanced load. An unbalanced load occurs when the impedances connected to each phase are not equal. This can cause current to flow in the neutral conductor, which can overload the neutral conductor and create voltage imbalances in the system. The neutral current can be calculated using the unbalanced neutral equation. This information can be used to select the appropriate size neutral conductor and to protect the neutral conductor from overload. The neutral current is the vector sum of the phase currents because the currents are alternating currents and have phase angles. The phase angles are due to the inductance and capacitance of the loads. The vector sum takes into account both the magnitude and phase angle of each current. If the loads are balanced, the phase currents will be equal in magnitude and 120 degrees out of phase with each other. In this case, the neutral current will be 0. However, if the loads are unbalanced, the phase currents will not be equal in magnitude or 120 degrees out of phase with each other. In this case, the neutral current will be non-zero. The cross-product terms I, IK, and IK represent the interaction between the currents in different phases. They account for the phase angles between the currents. They affect the magnitude of the neutral current. If the phase currents are balanced, these terms will cancel each other out. However, if the phase currents are unbalanced, these terms will not cancel each other out. They will contribute to the magnitude of the neutral current. Let's clarify the meaning of root mean square values. Root mean square values are used because the average value of an alternating current is 0. The root mean square value is a way to represent the effective value of an alternating current. It is the value of a direct current that would produce the same amount of heat in a resistor as the alternating current. The root mean square value is calculated by squaring the instantaneous values of the current, taking the average of the squared values, and then taking the square root of the average. The unbalanced neutral equation is derived from Kirchhoff's current law, which states that the sum of the currents entering a node must equal the sum of the currents leaving the node. In a three-phase system with a neutral conductor, the neutral conductor is connected to the neutral point of the source. The neutral point is the point where the three-phase voltages are equal in magnitude and 120 degrees out of phase with each other. The neutral conductor provides a path for the unbalanced current to flow back to the source. Without a neutral conductor, the unbalanced current would have to flow through the ground, which can create voltage imbalances and safety hazards. The magnitude of the neutral current depends on the degree of unbalance in the load. The more unbalanced the load, the greater the neutral current. The neutral current can be reduced by balancing the load. The load can be balanced by distributing the load evenly among the three phases. This can be done by connecting appliances and equipment to different phases so that no single phase is overloaded. The neutral current can also be reduced by using a neutral reactor. A neutral reactor is an inductor that is connected in series with the neutral conductor. The neutral reactor limits the flow of neutral current, which can reduce voltage imbalances and improve system performance. The unbalanced neutral equation is a valuable tool for electrical engineers. It can be used to calculate the neutral current in a three-phase system to select the appropriate size neutral conductor and to protect the neutral conductor from overload.